We'll start with questions. Last time we did a little recap of some of the big concepts and started wading into solving exponential and logarithmic equations. And I think we have, what do we have? Up to 70 now is the problem set. Yikes. Anything, any questions on things? Have we towed into this homework set yet to where we have questions about stuff yet? Anything you don't understand or any of that? It doesn't even have to be specific homework question, I guess. It could just be conceptual stuff. Yeah, Joe.
It's not about the homework.
That's okay.
For seniors,
yeah.
The final exam study guides due Friday, right? This coming Friday.
Yeah, your last day in class would be fine.
Okay. And then, so do we to give that to you, right?
Yes, and I'll paperclip it to your exam. Okay. So it'll come back to you with your, when you get your exam on the exam day, I'll have it paperclipped to it.
Sounds good. Okay, cool.
Yep, no problem.
Thank you.
Yeah, sure. Okay. Content questions, homework questions? Not right now? You can get to it? It makes me kind of scared, guys. Okay, that's fine though. No biggie. Let's pick up where we left off in section 15.4 is what we've been working on. So in section 15.4, we had talked about solving exponential and logarithmic equations. And we did some techniques therein. What we're going to be doing in the second half is looking at some specific application situations and solving using these specific applications. So we're going to give you guys a bunch of different models for these different situations, and we'll use these models to create an equation to solve. So our first model is about sound intensity. Does anybody remember the name of the unit that we measure sound intensity with?
Is it decibel?
Yeah, it's a decibel. That's right. And the abbreviation for a decibel is dB. The D for the prefix deci is lowercase, and the B for the bell is uppercase. That's weird, but that's what it is. So our formula is beta equals 10 times log of I over I naught, where the beta is the number of decibels. I is the sound intensity. And the unit for sound intensity is watts per meter squared. And I naught is a constant. So I naught is always 10 to the negative 12 watts per meter squared. So let's do an example here. All right. Given that the sound intensity of a city bus or where did bus come? Given the sound intensity of busy city traffic is approximately 10 to the negative fifth watts per meter squared, what is the measure of busy city traffic in decibels? Well, since we're talking about sound, hopefully it's pretty clear that I'm going to be using my sound intensity model. So what are we trying to solve for in this equation? Are we looking, is the question asking us for beta, I, or I naught?
One of the I's. We already got beta.
Since it's asking for a measure in decibels, we're looking for beta. Okay? Again, like it's just the decoding piece, that's why we're going through it. I really love trying to answer, even if the answers are incorrect, because what it does is it creates us an opportunity to talk about what your initial intuition was, so we can kind of correct those things before the test or the quiz comes. So really, even if you're wrong, that's fine. Shout out to your answer. What's your initial gut feeling? That's really helpful. It's good feedback for you. I think it helps, gives us something to talk about, so it's just not like watching Mr. Kulig do the problem with straight through. You know what I mean? So don't be discouraged on that kind of thing. Okay. So we need to fill in then values for I and I naught. What does our value for I have to be? Very good. And what's the value for I naught?
10 to the negative 12.
Yes, good. Remember, I naught is a constant.
So is it always 10 to the negative 12?
Yes. Constant means that it's always constant, right? That it's not a variable. It's always that number. The only reason that might that could feasibly change, and Grace, this wouldn't happen in a story problem that I would give you, would be like a unit situation where like we gave this thing in centimeters squared or something. So you'd have to make sure that your constant matched the unit of the other measurement. But like you could keep the constant and change that other, it'd be a units issue would be the only reason it would be different. So I'll just type this into our calculator then, exactly as it's written. Oops, well, I figured it out. 70 is what we're looking at. Feel good? No big deal, right? 70 decibels loud?
A little bit.
Yeah, it's pretty loud. It's not gonna like hurt your ears loud, but probably not very comfortable either. Okay. Another model that we have is using the Richter scale. What do we use the Richter scale to do? Yeah, it measures the magnitude of earthquakes. One interesting thing about the Richter scale is that it is logarithmic. What that means is that like a magnitude 3 earthquake is 10 times as powerful as a magnitude 2 earthquake. So imagine a magnitude like 8 or 9 earthquake is like, it's a lot of energy being released. So our Richter scale, R is just the Richter scale number. Oops, that's a name. Should capitalize it. A is the amplitude, and we measure that amplitude in micrometers. I think is that mu symbol is the prefix for micro. T is the vertical ground motion. At the position of the earthquake. Oh my goodness, Mr. Kulik, I buggered this all up. Excuse me. All right, so let's do this. So A is the amplitude. That is the vertical motion at the a ground motion at the position of the earthquake. Excuse me. T is the period of the associated wave measured in seconds. Then B is a constant that accounts for the weakening of the wave with increasing distance from the epicenter. So like we know for an earthquake, the further away you get from like where the actual plates are going crunching into each other that's causing the earthquake, like the earthquake is less strong as you get further away, right? All right, so let's again do an example. All right, the infamous San Francisco earthquake had a Richter scale magnitude R1 of 7.5. How many more times severe was the most severe earthquake ever recorded? That's the Chilean earthquake that had a Richter scale magnitude of 9.5. So to do this, I see that I have two earthquakes, right? Two different earthquakes. So I'm going to have two different equations that I'm going to build. One for each of them. So far, so good. So, what is this question asking now?
That's the difference between the severity of R1 and R2.
Very good. Specifically, the word difference there is what we're looking for. In mathematics, the word difference means subtraction. Yeah. Yes, very good. So we're going to do R2 minus R1 is what we're looking for. Everybody feel good there? So that means that I'm going to have log of A2 over T2 plus B minus log of A1 over T1 plus B. Everybody feel okay there? I basically just subtracted the two equations. So R2 was R2 was 9.5 and R2 was 7.5. And when I distribute my negative through, I get that. Okay. So I can combine some like terms, and I get b and negative b to cancel out. And then 9.5 minus 7.5 is 2. So far, so good. So I notice that I have the difference of two logs here. What property can I use in this case when I have two logs that are being subtracted? Thank you, the quotient property. Very good. Since these are fractions, I'm going to write it with the division symbol there rather than writing a fraction on top of a fraction, because I think it makes it a little easier to deal with here in a moment. Uh-oh. My screen go. Okay. Everybody still so doing okay? When I divide two fractions, how do I do that? Right, I have the division of two fractions going on here on the inside. How do we do that? Very good. So we flip the one on the right and turn it into a multiplication problem. Now we're going to make another assumption. Okay. So the t was related to the period of the earthquake. And the amplitude is like the vertical ground movement, right? We're going to assume in this case, since we're talking about the severity, that's really talking about the amplitude, right? When we're talking about how severe an earthquake was, it's like how much rocking was that building doing? You know, was the ground doing? You know what I mean? Does that feel plausible to you guys? We don't really care much about the t, the period, meaning like, you know, if it's moving up and down, how long is it going up and down for? You know, like to do an up and down. What we're going to do is we're just going to kind of assume that T1 is equal to T2. All right. Now I got to get rid of that log now. What cancels out a logarithm? This is what we spent most of yesterday kind of building at.
It was like something base 10.
It's an, okay. So it's an exponent base is what cancels a logarithm. Very good. The exponent base that we want to choose should match the base of the logarithm that we're using. What is the base of this logarithm in our problem? 10. How did you know that?
Because of the standard base for a log is 10.
Right. So if there's no subscript written, we know that it's base 10. So I'm going to do the exponent base 10 to both sides. Again, notice that I'm making that 10 really big so I don't confuse myself and actually accidentally mistake it as multiplication. I know exponent base 10 cancels log base 10. So what we're finding here is that the displacement of the Chilean earthquake was 100 times greater than the ground displacement was 100 times greater than the San Francisco earthquake. Woo! It's a lot, considering the San Francisco earthquake was pretty bad already. It's 100 times worse. Ay caramba. Poor Chileans. Okay. Another model is the pH scale. Did you guys use the pH formula in chemistry? Okay. So what the pH scale is doing is it's measuring the concentration of hydrogen ions inside of a solution, inside of a compound, right? So pH is a numeric measurement. What's the scale? It's like 0 to 14, I think.
Yeah.
That sounds right. And then like what? 7 is neutral. 0 to 7 are basic, and then 7 to 14 is acidic, I think is what the Is that right, chemists? Yeah, okay. And then here, this stands for concentration of H plus ions. And usually that's in, what is it, probably molarity is probably the way that we measure the concentration in here, would be my suspicion. Or maybe it's probably not molality. But again, the pH scale is another one where, you know, something with pH of, you know, like a pH of something with pH 4 is 10 times as acidic as something with a pH of 5, right? Let's look at an example. So we have a really sour lemon is found to have a pH of 2.2. So again, this is acidic. And a bottle of bleach is found to have a pH of 10.2. That's basic. What is the hydrogen ion concentration of the two items? Oops, negative. So if I do the acid first, to solve this, I would divide by a negative 1 to move the negative over to the other side. And then how do I cancel that logarithm?
You have to make the bases the same. So 10.
Exponent base 10 to both sides. Very good. Everybody okay with that?
Okay, Mr. Claude.
Yes.
If it's an LN, that's when you do the base E, right?
Correct. Oops. That's not the symbol I wanted there. Oh, why am I pressing second? Because I'm being, oh my goodness. I hate you. So we have 0.0063-ish. And then this is moles per liter, I think, is molarity, right? Chemists, is that right? Molarity is moles per liter. That's the unit. Does that sound right?
Sounds familiar.
I think that's right. And the other was 10.4 or 10.2. Excuse me. So yada, 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 I'm going to be doing the exact same thing, except I'm going to have negative 10.2 as the exponent, right? Everybody's cool with me just skipping all those steps because it's exactly the same steps as the previous ones. It just, you know what I mean, guys? I'll save myself some work. Whoa, wowsies. So that is going to be 0.38 or 398 times 10 to the negative 11. Yes.
Do you mean to do it 10.4?
Nope. Thank you. Ah, there we go. 6.31 times 10 to the negative 11. Or really, that's 0.12345678910 zeros. And then, woo! It's a lot less hydrogen ions there, huh? All right, so that's part A. And then part B says, how many times greater is the hydrogen ion concentration of the bleach than of the lemon? So we're going to have ten to the negative 2.2 divided by 10 to the negative 10.2. Since the bases of those exponents are the same, to divide them, I can just subtract the exponents. So I get to add 10 to the 8th. Yes, sir. So that means that that lemon has 100 million times the concentration of hydrogen ions than the bleach. Woo! That is a lot. All right. We got one more model. That's called Newton's law of cooling. So that, what this model is describing is if you take a hot item and you place it in a cool room, how is that temperature of that hot item cooling down over time? So T of T is the temperature of an object at time T. T sub M is the temperature of the surrounding. T naught is the initial temperature of the object. K is a constant, but that constant is specific to the object. So like a metal object is going to cool down differently than like, you know, a wood object or something, right? Take a hot piece of wood and a hot piece of metal and you put them in the same room. They cool at different rates because they're made of different stuff. That makes sense to you guys, I hope, right? And then T is just going to be time in minutes. All right. For all my chefs in the room, here we go with an example. A hard-boiled egg is heated to 96 degrees Celsius and then placed in a pot of 16 degrees Celsius water to cool. After 4 minutes, the temperature of the egg is 45 degrees. Find how long it will take in total to cool the egg to a temperature of 20 degrees, like room temperature. Ish. So pretty clear from reading this question, we should be using Newton's law of cooling on it, because we're talking about cooling an object down, right? So when I read this question, I have the initial temperature, the temperature of the median, we have a value for little t. But what we don't have anywhere in here, well, I guess let's keep going. What's this? This is like a t of t. I guess it's specifically t of 4. And then this is some other t of t where we don't know what the t is, right? Since it's asking for how long. Is everybody okay with just kind of unpacking where these numbers would go? What value do I not have anywhere, or that appears in my formula but doesn't appear in the question? I don't have that constant given to me anywhere in the question, right? So when I read this, this feels like, okay, I'm going to use the first part of this question to figure out the value for k to complete my model. And then in the second part of the question, I'll use my completed model to answer that, to find the little t to answer that situation. Does that feel okay to you guys? So I'm going to kind of treat this as two parts. I'm going to do the green piece first. So it says here my t of 4 is 45. the Tm is 16. Oh, yeah, that's a minus sign, Mr. Kulik. Did I write a minus sign up here? Oh, good. And then my Tm, and then my little t was 4. We feel okay with how I plugged everything in there? Again, we're solving for k. So let's see. First thing we should do is subtract 16 from both sides, right? And then I combine some like terms there. Everybody feel good? I'm going to divide now both sides by the 80. Sound good? And now how am I going to get rid of that exponent base of e? What's going to cancel out an exponent base? What cancels out an exponent base? No, not a square root. Not another exponent. What have we been studying this chapter? A logarithm. Okay, so we have lots of possible logarithms. Which base would I want for this logarithm? Base e, because it matches the exponent base in question. What is the symbol for log base e? ln. So I'm going to do the natural log of both sides. And then the last step to get the k by itself would be to divide both sides by 4. I'm going to write it as, or negative 4, I guess I should say. I'm going to write it, though, as negative 1 over 4 times rather than divides by, because it's a little bit neater when I write it on my paper. It's doing the same thing, though. So I get 0.254-ish. Okay. Now I'm going to probably want to hang on to all those. Well, that's fine. So that's like doing the green part of the question. Now to do the blue part of the question, we're trying to solve for t in that part. So we want to know the T of t is 20. The surroundings are still 16. The initial temperature was still 96. My K is this 0.254, and I'm looking to solve for T. So we'll start by subtracting the 16 from both sides. I simplify the 96 minus 16. I'll divide both sides by 80. I'll note that I could reduce that fraction, but I don't really care because eventually it's just going to go into my calculator anyway, so whoop-diddy-doo-dah. What I'm more interested in right here is getting rid of that exponent base of e. What do I need to use to do that? Which one?
ln.
ln. Very good. I heard somebody say log, I thought. I just want to make sure that which log we're using. And again, you can use any log, but like the arithmetic becomes, or the additional like simplifying becomes kind of crappy, that you have to jump through a lot of extra hoops if you don't match the log base to the exponent base. But there's no reason you can't. It's just not very efficient to do it that way. Back when Mr. Kulik was a student and it wasn't easy to just do any log you wanted on your calculator, we did do those sorts of things because, yeah, of course. But you guys don't have to worry about that kind of thing now. So there's that. And then the last step would just be to divide both sides by the negative 2.54. I'm going to write it as multiplying by a reciprocal. So I'm going to have 1 over the negative of my previous answer times the natural log of 4 over 80. I want to point out too that I'm using all of the decimal places for my previous answer when I'm doing this. I'm not just using 0.54. If you tried to repeat this using just 0.5 or 0.254, you'd get a slightly different answer, be a little less accurate, but like not a big deal. But if your answer doesn't match exactly the one in the back of the book when you do a problem like this, it's likely because you rounded that k and then differently. All right, so we get about 11.81 minutes. I guess if you want it to be really precise, like what's 0.81 of a minute? About 49 seconds. So 11 minutes and 49 seconds. If you wanted to do that, 0.81 is fine with me. You know what I mean, guys? All right. This feels like our stopping point for today because I, quite frankly, don't want to get into the next section yet. That feel good with yous? The next section would be the last section of chapter 15, just as a heads up. So juniors, we will be taking our chapter 15 test probably next week. Because we'll finish, you guys will do 15.5. It's probably a 2-day section and then a review day. Probably the end of next week or the week after, depending on how things fall. Just giving you the heads up. At this point, though, you guys can go now all the way to 98. No, we already done to 98. What am I doing here, Mr. Kulik? What? No, we were already to 98 before. Let me look here. You know, you just get confused sometimes. Okay. So we can go all the way to 138. This one is going to go on the 5/8 problem set, though. So for this weekend's problem set, we're going to stop at 98 because that feels like enough problems for this one. Okie dokie.